Hello and welcome to the Sustainability Seminar Series of the KIRAN PATEL Center for Sustainable Development at IIT Gandhinagar. Today we are pleased to welcome Rajendra Bordia, who is a professor of material science and engineering at Clemson University, and currently also a guest professor at IIT Gandhinagar in material engineering and KPCSD. Most creditably, I guess Bordia is a graduate of IIT Kanpur, B.Tech, where he was my batchmate and sometimes tutor also. He went on after there to a lesser institution, which is Ivy covered, Cornell University, where he did his master's and PhD in materials engineering. Bordia's research areas are complex materials for energy, extreme environment, and medical applications. He has authored or co-authored 170 publications, and today he's speaking to us on critical and enabling role of materials in carbon neutral energy. Bordia.
Thank you very much, Achal. Pleasure to be here at Gandhinagar and participating in this seminar series. I've been coming to IIT Gandhinagar for almost more than 10 years now. The first time I came here was in 2012, and it has been a pleasure to see the campus evolve, see this new campus formed, and have this long engagement with IIT Gandhinagar. And actually, there's also a pleasure and first time in my life to be introduced by somebody that I have known for over 40 years now. So thank you, Achal, for the invitation and introduction. So I'm going to talk about these topics. Going back, as Achal mentioned, I want to sort of present to you first as a starting point the problem that we all are very aware of, but in the context of, first in the context of what the current energy conversion technologies have done to create that problem, so to speak, and then focusing on some of the both short-term and long-term solutions that in which a class of materials that I've been working on, just ceramics, play a very critical role. So although the title is a little bit more general in terms of the enabling role of materials, but I'll focus it on more on ceramics. So that, this is the outline. Of course, most of this, the first part for most of you will be very introductory and elementary, but I just want to set the stage using that. And then the focus will be much more on the second part, on what some of the enabling solutions that we are able to achieve by using advanced materials and particularly ceramics. Okay, so again, not to belabor the point, but now it has become extremely clear. These are some quotes directly from the IPCC's summary statements. The first one was a long time ago, now 12 years ago, in which they, for the first time, sort of, this group proposed that the global warming or the rise in temperatures are due to human activity. So quite a strong statement coming from a group of essentially sort of almost a semi-political body kind of a thing. So these were administrators, policymakers, etc., and actually representing more than 100 countries. So for them to agree on such a strong statement meant quite a bit in 2020. And actually, as you know, they even won the Nobel Peace Prize for that particular year in that particular year. Since then, this group has been meeting every 2 years, coming up with similar, concise, but important statements. This one was the most recent one, in which they are starting to talk now about also the adverse impact of these changes in the temperature, both on the human system and the natural non-human system, right? And again, this is quite dramatic again for them to make statements like this, that the most impact or the most significant impacts are in the most vulnerable parts, both in the natural system and in the human system. Well-known data that they have used to come up with these statements, because this group also consists of eminent scientists. So they've been looking at rise in the mean temperature, global sea level rises, shrinkage of the snow cover, etc. So all the data that go into these kind of estimates and projections. This one is quite dramatic, and I'm sure many of you have seen it, but this is the global average temperatures over a very long period, starting almost 150 years or more. And what they're trying to point out is that the temperatures are rising quite rapidly, particularly in the last 50 plus years. And if you try to sort of fit the data points are these black ones. The yellow bands are the uncertainty in the data. And as you can see, initially there was a lot of uncertainty. Now it has become quite refined. And what they're trying to show here is that if you try to fit, for example, the last 10 years or the last 5 years, then the slopes of the shorter time period are steeper than those for the longer time period, which sort of basically is telling you is not only that the temperatures are rising, but they're rising faster. And in fact, the warmest 10 years have all been since 2005. So it's quite a dramatic realization that all these things are going on. But again, all of us hopefully have seen data along these lines. So this is actually from a science and to some extent engineering point of view, also quite an important point that I want to make here is that actually this is not something that is very new. People have been thinking and talking about it for a long time. But it so happened that until about the 90s, there were these two communities that were sort of somewhat separate, and they were not really communicating with each other. One community was of the climatologists and the weather scientists, for example, who were keeping track of data that I just showed you, the temperatures, the sea level rise, et cetera, et cetera. And then there was a whole different community of atmospheric chemists, right? And they were monitoring the changes in the Earth's atmosphere, also over reasonably long period of time. And so they were looking at data along these lines that, they were carbon dioxide, for example, the concentration of CO2 in the Earth's atmosphere had rapidly increased in the last sort of 50 odd years, 100 years or so. Similarly, methane, nitrous oxide. But these were two separate communities. And, starting in the 90s, they started talking to each other to see if there was a correlation between these two different data sets. So again, for scientists, it's important to know that sometimes we need to go beyond our boundaries or things that we are comfortable with and talk to somebody else who possibly might have an explanation for what we are observing. And that then led to things like this. This is, again, a very large effort by many, many scientists and institutions and collaborators and groups. So what they were trying to do now is to use the data on the constitution of the atmosphere to try and see if that could explain the rise in the temperatures. Right? And these are the various models that they came up with. So for example, and they took all kinds of factors into account. So I won't go through all of them, but again, the black data points are here. This gray line is the model that fits the data best, right? So it's the best fit to the data. The red line is that if you only look at the Earth's atmosphere, right? Nothing else. So the data that I showed you, CO2, methane, nitrous oxide, that kind of stuff. Then you see that actually that overestimates the actual rise in temperature. And that is because there are some other things that really reduce the temperature. Like for example, this one is the most dramatic one, which is the aerosols in the Earth's atmosphere, right? So particulate material, because it reflects sunlight back. So that actually leads to cooling. But then if you put everything together, then you get fairly good fit. These are the natural phenomena, things like volcanoes, solar activity, etc. And they have some effect, but really quite small. So again, very clearly, the changes in the Earth's the temperatures are due to human activities. They're due to the greenhouse gases and to the aerosols. One goes positive, other negative, but still the much larger rises are due to this again. So very good science that was done on this. So yeah, so again, just some more statements from there. Again, in 2020, they basically, the word was, and increasingly people were getting convinced, but unfortunately, to some extent, actually from the country that I professionally work on now, there were people who, for political reasons, did not want to believe this science. And even today, they don't believe the science. So they were sort of quite, no, sorry, where did I go? So they were quite clear in their statement that with more than 95% certainty, and for scientists to say that, you're quite certain that these changes are due to human activities. And now, as I said, continuing on, they've been making statements that it's not just that the temperature rising, they have all kinds of effects on sea levels, snow, and most recently, they've started talking about effect on natural systems and whether there is, we are getting to a point where the corrections might be very difficult to make. So yeah, so just last couple of slides more on this background part. But one of the things is that if we now believe that the models have become good enough that they can predict the past temperature patterns, then we can also take them forward and see what would happen in the future, right? And that is what this data is here. So up to this point, for example, somewhere around here is where we are. And these models have now predicted what would happen by 2100 under different scenarios. So these scenarios being, we continue to emit greenhouse gases at the rate that we are emitting now, actually increasing rate, as I'll show in a minute, or we sort of stop it completely, which is this model over here. So even if we stop emitting greenhouse gases completely, you'll still see a slight rise in temperature because the gases last for a long time in the atmosphere. But again, if we are, the worst case scenario would increase the temperature by about 4 degrees over the pre-industrial times, right? And we are only about half a degree or so since then here. So quite dramatic changes could occur unless we are careful as a whole society. Again, I won't sort of read all these things, but they're not just temperature rise, but effect on all things, all weather-related phenomena, quite dramatic impacts. So let's now sort of come to the key point that I want to make, which is this connection between our energy technologies for the last 150 years and this rise in greenhouse gases. And this is, maybe we should start with this curve here. And these are emissions of CO2 as a function of time, starting from about roughly the Industrial Revolution time. And you can see that the primary contributor to the greenhouse gases was coal at that point, burning of the coal. And starting from about the 1900s, oil and gas also came online. And this is the total emissions. The blue one is coal. And you can see that coal has started to flatten out a bit, but the oil and gas are still going quite a bit strong. And this data is probably actually, again, for such long-term data, these kind of correlations are quite amazing. So this one is the amount of primary energy that our planet consumes and the CO2 emission. And they're just, perfect one-to-one correlation showing that essentially all the energy conversion technologies that we have or we use predominantly have CO2 emissions associated with them. Anybody wants to guess what this flattening was here due to? 1990 to 95, what major event occurred during that time geopolitically? What's that? It was the first Gulf War, right? So this is, and that time actually the oil, there was a big oil shock across the world, which led to actually a decrease in oil consumption, which also led to a decrease in CO2 emissions. So very directly correlated. Actually, once we collect the data for 2021, also you will see a similar slight decrease in it because of COVID at that time. So, whoop. Unfortunately, actually, we continue to use a fair amount of these fuels. Coal still worldwide is about 27%, oil is 33%, and gas is 21%. So over 80% of the primary energy that we still use is coming from these three fuels. Everything else is, 20% or so, including renewables, hydropower, and even nuclear, for example. So These are the three big ones that contribute the greenhouse gases. And what we call as the modern renewables, solar, wind, and geothermal, they're actually less than 10%. Biomass is actually still quite large. There's a lot of energy is from biomass, and it is renewable, but still in the next. So now, why do we need to consume so much energy? And I thought that I would show you this data here, which actually correlates the GNP, per capita GNP, to the per capita energy consumption. And this is actually many countries have plotted on this. And if you were to draw a straight line through it, it sort of looks like a correlation between them. And indeed, it is true. As economies consume more energy, their per capita GNP increases. But there is very interesting outliers, and those are the ones that I want to point out. So, compare, for example, Russia and Japan, right? The two have roughly the same amount of energy consumption, but Japan's GNP is almost an order of magnitude more than that of Russia. So what this tells you is that there is an efficient way to consume energy and there's an inefficient way to consume energy, right? And countries that are sort of on the development path need to keep this in mind. So it is not just that you need to consume more energy to have higher GNP. There's a way to do it more efficiently, for example, right? So these are sort of the kind of lessons that we can learn from this. There are more sort of examples like this, but I just wanted to highlight those two. And then there is this last data point about this, again, correlation between quality of life and energy consumption. And this is from United Nations. And they do something called the Human Development Index. And this measures things like lifespan, access to healthcare, access to education, sanitation, etc., as a combined measure for Human Development Index. And what this shows is that, once again, as the energy consumption increases, this HDI increases. But this curve actually is, for engineers and scientists who would see this, this is an asymptotic curve, right? The initial slope is very high. So small changes in energy consumption from the low end can give you big improvements in HDI. But once you start to get somewhere around here, there's diminishing returns, right? So really, you don't get a lot better quality of life just by consuming more energy when you are way up there on the curve, right? So once again, countries like US, etc., are outliers on this, compared to, for example, say Germany, which has similar HDI but much lower energy consumption, for example, right? So once again, point being that there are ways to consume energy without wasting it, so to speak, and have the biggest impact. Okay, just to summarize this, I hope I have convinced you that there is a direct correlation between the changes in our Earth's atmospheric chemistry and our energy consumption, or the way we are consuming or using energy, and the changes in the Earth's atmosphere chemistry leads to changes in its climate. And you could argue that energy consumption is very important to human societies, developing societies. And we know that for the access to energy, countries have gone to great lengths, including several wars in our own lifetime, which have been due to access to energy. So war, environmental devastation, etc., just for access to energy. And then again, the current energy technologies are definitely things that we need to change. Okay, so now I'll move on to the more of the technical part of the talk that is sort of related to the kind of work that we do in my group. I will talk about the role of ceramics in this transition to low carbon energy technologies. So, one of the major usage of fossil fuels is in transportation technologies, right? Diesel, petrol, kerosene, etc. And the reason for this is actually in this chart. And this one I took from a colleague of mine who is a chemical engineer. And the point that this colleague was trying to make is that he was saying that if you took the brightest chemical engineers and you put them in a room and told them to design an ideal transportation fuel, most likely they would come up with a hydrocarbon of some kind, an 8-ring or a 4-ring hydrocarbon. And the reason for that is that these fuels, hydrocarbons, have some of the highest energy density. That is, they have the highest amount of energy per unit mass, right? So as a result of it, you don't have to carry a lot of fuel if you want to go from one place to another. Otherwise, you would just be transporting the fuel. You will not be transporting the cargo, right? So that's why hydrocarbons are so important. Look at this, gasoline, kerosene, almost 50 megajoules per kilogram. Very, very high energy density. The only things that are higher than this, of course, is something like hydrogen, which is about 3 times higher than this. But that is the reason, of course, hydrogen is very hard to carry around as a liquid fuel. So because of this very high energy density, our transportation systems are based on these liquid hydrocarbon fuels, okay? So, but of course, if we want to get rid of them, if we want to go to carbon neutral transportation fuels, then we need to come up with another way to do transportation. And of course, one of the alternatives that is being talked about quite a bit these days are batteries or electric power cars, vehicles, etc. But unfortunately, you look at the current energy densities of the batteries, it's actually quite low, right? 0.5 to 1 megajoules per kilogram. Look at gasoline, it's about 50 times bigger than that, right? So as a result of it, in electric cars or electric vehicles, a lot of weight is taken up by the batteries. In fact, one of my, one could argue actually that an electric vehicle is really a vehicle to carry the batteries, because the weight of the batteries is more than the weight of the cargo that it is carrying, right? Of course, that doesn't happen with the gasoline-powered vehicles, because there, the weight of the fuel is a lot less than the weight of the person that is sitting there or the cargo that you're carrying. So this is a challenge. I mean, of course, we have to move to these carbon neutral technologies, but that requires significant improvements in this. So hydrocarbons are the fuels of choice. How can we replace them? There's a lot of interest in electric vehicles and in hydrogen vehicles, and I'll talk about both of them. The advantage of these is that they are primary fuel flexible, in the sense that you can use renewable electricity to generate both electricity, of course, and also hydrogen. Again, people claim and they advertise that these are zero emission cars, for example, but it is really truly zero emission only if the electricity that you're putting into it is from a zero emission source. If you're burning coal to make the electricity, then the car is no longer zero emission, right? It's just displaced emission there. Of course, lots of work has gone into battery technologies. The old batteries used to be the lead acid batteries. They are much heavier than the lithium-ion batteries, so nobody really thinks of them for transporting for electric vehicle batteries. The lithium-ion batteries are the ones of choice right now, still very expensive, still not enough energy density, still fairly slow charging. So all kinds of challenges exist with them, but there's a lot of interest in them and a lot of work going on in this area. In my group, we have been working on lithium-ion batteries also for a few years now, and our focus has been exclusively on 2 aspects of it. One of them is to increase the energy density, and the second one is the faster charging. And we have been using an approach of microstructure design. I won't go into a lot of details on it, but happy to talk more if you want. So we have been making these electrodes for lithium-ion batteries with engineered microstructures, engineered porosity, which allows us to access the entire electrode at the fastest charging rates. So just to show you some data on this, so if we have regular kind of porous electrodes, then when we charge it at a fast rate, the capacity drops by about a factor of 2. With these engineered porosity electrodes that we've been working with, even at the fastest rate, the capacity drop is only about 5%. So significant improvement in the retention of the capacity at fast charge discharge rate. So we're continuing to work on it. There's a lot of potential to further improve it. Now we are using simulations to design the optimal microstructures and then ways to make those microstructures. So it's an ongoing project. So that's, we'll keep the transportation on the side for a while. I'll come back to it towards the end when I talk about hydrogen, because in my opinion, that's actually a very attractive fuel for transportation. So we'll come back to that later. But let's now switch gears and talk about the primary electricity that we use. Again, you can sort of think about what are the major uses of power or energy in our lives, and you can sort of divide it into one for transportation and the other for electricity. If we have good fuel for transportation and good fuel for electricity, then we are sort of basically covered. Now, in the case of electricity, there are lots of ways that we can reduce the CO2 emissions, and many of them have been practiced and are continuously evolving. One is just energy conservation. We actually do waste a lot of energy. There has been estimates that somewhere in the range of about 20 to 30% of the energy that is produced, electricity that is produced, is essentially wasted, either in transmission losses or in using them where you don't need it, leaving lights on, for example, when you don't need it, etc. So there's a lot of advantage there. And more recently, there have been much more efficient electric light bulbs that have come up. This is a huge improvement, actually. They have reduced the power consumption by about 20 to 25%. LED bulbs, for example, CFL was older technology, but LEDs now have reduced power consumptions by about 50% or so. So significant improvement there. In terms of machinery, mechanical engineering, there's a lot of focus on lower friction. It turns out friction is a huge sink for energy. But leaving the energy conservation for the side for the time being, let's talk about the conversion from fossil fuel to electricity. That's the way our society is run right now. Coal, gas are the primary sources to produce electricity. And there is a lot of room, again, to improvement in these areas, primarily in terms of turbine improvements. Right now, actually, the performance of turbines is limited by the peak temperature that they can go to due to materials limitations. So there's been a fair amount of activity in replacing the metallic materials by ceramics in order to get 5 to 10% more efficiency. And that might sound very small, but a 1% efficiency improvement in gas-fired turbines reduces CO2 emissions by 5 million metric tons. That is how many gas turbines are working around the world. That is the impact of small improvements in efficiency. So things that might seem small, a very large impact. And in my group, we've been working on this also for some time. Another approach that we've been working on are the solid oxide fuel cells, which give you almost double the efficiency of a gas turbine, right, for the same fuel. So here are some examples of the work that we have done over the years on improving the efficiency of classical thermal power plants, from coal-fired power plants to gas turbines. We've been working on developing these ceramic coatings on metallic systems that let us go to higher temperatures, roughly about, in the case of turbines, the improvement is roughly about 150 to 200 degrees C by using about 150 micron thick coatings of ceramics, right? So the second area that we have been working on in my group is on solid oxide fuel cells. These are electrochemical devices that convert chemical fuels like methane, for example, directly to electricity without burning it. And the efficiencies are very high, up to about 75 to 80% efficiency. And there's a lot of interest in them, also a lot of challenges. So we have been working on their processing, and I'll show you the final set of results on this rather long project that we did with a company. This was a company that we worked with, Saint-Gobain. It's a big French materials/glass company, big operations in India also. And they were making these solid oxide fuel cells in which the performance was, for all of them that they made, there's a whole stack of about 10 or 20 stacks that they made. And in all of them, the performance was below their target, where they would have pass-fail criteria, both for their power density and for open circuit voltage. We worked with them for many years, looking at their production processes, trying to identify what were the reasons for these low performance, because the material system that they were using was a good material system. And we found that because of the way they made these, they had these defects in their fuel cell. These are due to what we understand well is due to constrained sintering, where you are trying to densify these different materials together, and that results in cracking of these kinds, and because the processing had not been optimized. And these cracks actually serve as essentially short circuits. So the fuel just goes through the cracks rather than doing its electrochemical work. And as a result of it, the power performance is rather low, right? So we worked on this with them, went through their processing route step by step, and were able to actually fix it. And then they were able to make these fuel cells in which all of them, with this modified processing, classical material science kind of an approach, all of them with this modified processing were able to meet both their power and their open circuit voltage requirements. A significant improvement, but it took, again, 2 years of sort of very careful materials kind of research to try and find out which steps they could change and what impact they would have. But it's a successful project that they were able to implement. So now sort of coming to essentially what everybody believes is the ultimate solution to the electricity challenge, and that is to use completely renewable sources, completely get away from fossil fuels. So those were all sort of that I proposed so far, improved efficiency turbines, solid oxide fuel cells, etc. Those are all sort of transitional intermediate steps. Eventually, we'll need to go to this. Sorry. So you all are well familiar of the increasing interest in wind, solar, and also bioenergy here. And they're sort of rapidly being implemented on lots of wind farms. So almost in the current mix, wind is about 26% of the renewable energy production. Solar is about 13%. The majority continues to be hydroelectric power, at about half of all the renewable power. But again, there's a lot of potential. Solar and wind together can, hundreds, if not thousands of times have more potential than what we need. 17 terawatts versus 90,000 terawatts for just solar. So there's a lot of potential in these renewable energy systems, and there's a lot of activity, a lot of research is being done, a lot of developments being made. In my group, what we have focused on is this part of the solar, which has not received much attention, which is the solar thermal part, not the photovoltaic part, right? And the solar thermal is also quite important because roughly about 50% of the incident radiation from sun is in the higher wavelength, right? Infrared or higher. So these are not visible wavelengths. These are the wavelengths at which the photovoltaic cell doesn't do anything. And in fact, this part of the spectrum of the sun is harmful to the photovoltaic because it heats up the solar cells. And when the solar cells get hot, their efficiency drops, right? So in my group, we've been focused on trying to find ways to use the solar thermal part or the thermal part of the solar spectrum. And of course, there are people have been doing this for a while, all the way from things like solar cooker. We have a few on the campus here that you see around one of the cafeterias. Solar water heaters are quite common. And so are these solar power plants. There is a fair number of them in operations, particularly in desert kind of areas. This one is from California. It's one of the oldest working solar thermal power plant. I think it's 400 megawatts, 350 megawatts. Heats up water up to 450 degrees C and then generates steam, high pressure steam. And then you just run a classic steam turbine from it to generate power. And again, it has been running for a very long time. So there are lots of examples of this. These parabolic ones get temperatures much higher. You can get much more power out of them. So there's a lot of activity in this area also, but still it has remained somewhat less thought of, so to speak. In my group, what we have focused on are developing ceramic materials to store solar thermal energy. That's another good advantage of this particular approach, is that you can store heat, right? You can't store light, but you can store heat. So photovoltaic solar converter, right? Solar power plant would have nothing to produce during the night, but in a solar thermal one, you can store heat in some thermal storage and then run it in the night. And one of the good thermal storage that we've been working on, so this is the concept of these solar thermal power plants. You use reflectors to heat up some solar receiver. And with this receiver, then you can store heat as either hot air or a hot fluid, for example. And then when you need it, you can run the turbine. You can generate steam and run the turbine, right? So it's not only a way to generate electricity, but it's also a way to store energy during the time when the sun is not shining, for example. It has those advantages. Again, we were primarily on the materials. So what we have been working with is the design of efficient solar thermal absorption materials. And it turns out that one of the ceramics that we work on, silicon carbide, is an amazingly good solar thermal absorber. This has actually almost 100%. This is absorption coefficient. It has almost an absorption coefficient of 1 across the entire wavelength of the solar spectrum. So essentially all the solar energy that falls on this material gets absorbed by this material. It's not reflected, it's not transmitted. So it's a great absorber material. And we have been working on designing the microstructure of this material so that we can get high absorption, but also enough surface area so that we can release the heat when we want it by doing this energy exchange. And we've been making these kind of porous structures out of silicon carbide, designing them for the optimal performance. So now let's come back finally to this energy storage challenge again, because again, any of these renewable sources of energy are intermittent. So you need to have some kind of a storage. Lot of activity in the area of batteries. We already talked about the lithium-ion batteries. There are many other chemistries that are being developed and investigated. All kinds of ions, zinc ion, aluminum ion, sodium ion, etc. And in many of them, which I'm not showing here, but ceramics play quite an important role. But so many of them, ceramics play a critical role. What I want to focus on is this green hydrogen. Hydrogen is another way for us to store electricity. What I mean by this is that, actually, before I go there, hydrogen actually in the new energy spectrum, hydrogen, in my opinion, will play an important role because you can do three things with it, which uniquely hydrogen is capable of doing. One is that you can power transportation. You can actually run cars and your vehicles with hydrogen. There are hydrogen-based fuel cells. You can also burn hydrogen, right? Generate water. So it could even be in a combustion engine, you can use it. So it can be used for powering transportation. And I don't know if you remember that chart that I showed you a long time back. Hydrogen has actually the highest energy density, right? It's 142 megajoules per kilogram. So on a weight basis, it's a great fuel for transportation, right? You could even actually run aircraft with it. I mean, there is all this scare of Hindenburg and not putting hydrogen in an air flying object. But hydrogen is relatively safe and you can use it to run any kind of transportation system. It can also, and this one is not paid much attention to, but hydrogen is also a great reducing agent. It's actually better than carbon, right? So you can use hydrogen to reduce iron oxide to make steel. You don't need to burn coke for that. So again, hydrogen is a great reducing agent for these chemical processes. And finally, you can use it to store electricity, which I'll show you in a minute. So the concept of using hydrogen to store electricity is shown here. Let's say, for example, you produce electricity from renewable sources like wind or solar. And if you have more electricity, which you can either store it on batteries, but batteries are expensive. So what you could do is you could use your excess electricity to do electrolysis of water, generate hydrogen, and then store hydrogen. Just store it, right? And then when you don't have your sun shining and when you need electricity, you can use the hydrogen to generate electricity. You can basically, as I said, you can burn hydrogen in a turbine to make power. You can also use it for powering transportation, or you can use it for industrial. So in a way, hydrogen is a very flexible fuel to get around many of these challenges that we have for carbon neutral economies. There is a significant and growing interest in developing turbines that can burn hydrogen. So instead of natural gas, for example, people would like to burn hydrogen to generate power using turbines. And it turns out that there are challenges. The two biggest ones are that with hydrogen, you get much higher temperatures in the turbine. And the second thing is that because the only combustion product is water vapor, the amount of steam or the partial pressure of steam is much higher in the turbine. And steam is very corrosive to metals, and the higher temperature means that most metals cannot be used. So what the industry is looking at are ceramic materials. There's a lot of interest in silicon carbide composites, making actually turbine components out of this composite. It has the capability to go to the temperatures that are needed and the loads that are needed. The problem is that silicon carbide itself oxidizes in the presence of steam. It becomes silicon dioxide, and then silicon dioxide in the presence of water vapor converts to silicon hydroxide that can just be, it's a vapor, so it just gets swept away because of the very high velocities in a steam turbine. So in my group, we are working on oxidation resistant coatings for silicon carbide. And this is the concept that we've been working on. You have a silicon carbide composite, and we put this graded coating on it that ends up being an oxide coating, which is resistant to oxidation. And again, I'm going to show you just one set of results on it. So this is the whole program in which we develop the compositions of those coatings, the gradients in them, develop processing approaches to make them, and then we characterize the performance of these. This was in collaboration with GE, and they took our coatings that we put on the silicon carbide and tested them in these very extreme thermal shock kind of setting, where essentially on one side, you have a fuel torch, which was at a temperature of 1400 degrees C. And on the other side, you have just cold air. So it's an extreme thermal shock, and these coatings survived these tests. But the more important result is here, which shows that when we did not have any coating, because of the high velocity steam, you got significant mass loss. So these are only hours. And in these hours also, we got about a few % mass loss from the silicon carbide. By putting the coatings, we were able to reduce so this is actually the corrected data. So this is without coatings, this is with coating, and the reduction in the recession rate was about a factor of 5. So it's sort of early on in this project, but already we are showing that you can dramatically improve the oxidation resistance of silicon carbide by putting these kind of coatings. Okay, let me just conclude now. There is this argument that is, and a very convincing argument, absolutely, continuously made by several countries, including India, which is that, we are not, or we were not responsible for the problem that has been created, right? And it's very true. The hard data shows that if you look at the total CO2 emissions in the last 250 years, India is fairly low. Where is it? Here, right? So 2.5% or so compared to, say, almost 10 times more for the US, 25% for the US. So even though with much larger population, the contribution to CO2 emissions are very low for India, very true. Similarly, even if you were to look at the current per capita CO2 production, once again, India is about 1/10 of where the US is. So even now, we are not, in India, we are not generating as much of the greenhouse gases, right? So absolutely true. The responsibility for messing up the environment lies elsewhere. Definitely doesn't lie with us. However, I would argue that the opportunity to do something with it lies with us also, right? I think this is a great sort of inflection point in the history of scientific and technological evolution. I think we are going to have to move away from the technologies that were developed in the first industrial revolution and move on to something different. So this is an opportunity for, especially for countries like India, which has a huge talent of manpower, bright, intelligent people. And there is an opportunity to come up with a different set of technologies which have lower CO2 footprint. And I think there's a lot of opportunity in this area, both in the industrial area, agricultural, residential, energy conversion, energy storage. All of these are completely open fields right now in which there is, in a way, very little competition. So we could actually do something rather innovative in this area. With that, I conclude. I hope I have tried to make a case that the way we have been doing things has been a problem, but it's also an opportunity now to do things differently. And some of these kind of, all of us who are in science and engineering have a role to play in this one. I've tried to show you what we have been able to do with the ceramic materials, which is our area of expertise, but there's opportunities for all fields and domains to contribute to this. So significant improvement opportunities increase for energy conversion, energy storage. And in our group, we are trying to capitalize on some of these opportunities. These are the students and postdocs who did all the work that I showed you. Some of you might recognize this guy. He's got his Ph.D. at IIT Gandhinagar, and then he worked with me as a postdoc. He's now actually working for GE in Bangalore. So he's a research scientist for GE in Bangalore. Okay. So thank you very much for your attention. These are the people who funded this research.